Okay, first thing we're going to talk about today is distributed loading. And really what distributed loading is for our terms is basically loading that acts over a surface or along the length of a beam. Okay, so essentially that's what I have here, right? I have just a beam supported here, and this W represents a loading. So this would be equivalent to, if you've got some sort of large object sitting on top of it, that doesn't act simply at a point, right? That acts over the area of the object, okay? So if we look at how that distribution of the forces occurs, over that length, that's what we call a distributed load, okay? So we're going to basically use equivalent system centroid methods to deal with this, because essentially I'm going to take this distributed load, this load over area, which really all forces are like this, okay, but we want to represent it as a point force like we've been dealing with up to this point. And we do that essentially using the, how we figured out centroids, okay? So the magnitude of such a force is basically summing up all of these tiny little w's over the x length. Okay, so sum of an infinite number of forces is simply an integral of all of these forces over my x-axis. Okay, and essentially the definition of an integral is just the area under the curve. Okay, so I can find the magnitude, a resultant magnitude, by adding up all these forces, which is equivalent to the integral, which is equivalent to the area under the curve. Okay? Now, find the location. I mean, it's basically just going through the centroid, right? We're basically reducing this distributed system down to a single force that passes right through the centroid of my area. Okay? Which, again, is defined as, x dA over dA. I mean, that's how we figure out the location of a centroid. So if you see a distributed load, the area under that curve is what the force will be, and then just find the center of that and put that magnitude of the force going right through the centroid of that. Okay. Now, moving on to kind of a different topic, we want to talk about internal loadings. And really we've seen this previously back when we talked about the method of sections for trusses. Okay, a little bit different here is we're not simply looking at two force members. So for example, I have a cantilever beam here. I've got a couple of forces acting on it. I, again, have two forces over at A and a bending moment, or a reaction moment at A. And essentially I want to figure out what the internal loadings at B are. So what I do is I cut through A, and I separate out exposing internal loads. Now, because this is not a two-force member, right, I have P1, P2, and then all these reactions over at A. Okay, it's not simply just the normal force. Now, the normal force is a part of it, the force coming out of the body, but I also have a shear force V and a bending moment M. Okay, so I can solve for these by looking at one side or the other, just like I did with the method of sections, summing the forces and summing the moments, setting them equal to 0, and solving for these internal loads. Okay. Now, we do have a sign convention. I wouldn't get too worried about it, but just so you know the sign convention. For a normal force, our sign convention is if it's under tension, it's positive. Okay. For our shear force, it depends what side of the face you're looking at. Now, again, because of Newton's third law, they have to be equal and opposite depending on which side you're looking at. Okay, so if V is downward, okay, basically on the right side of the face, or if I look at the left side, it's downward. That's a positive. Okay, if I look at the right side half, where V is actually acting on the left side, we call positive up. Okay, and my bending moment, again, Newton's third law, they have to be in different directions. Okay, we call a positive bending moment one that essentially causes the beam to bend upward. Okay, so that's the sign convention. Again, it's not super critical at this point to get those signs right, but that's how you do that. But again, we treat this just like a method of sections, right? find your reaction forces, make a cut, separate them out. Now instead of just having a normal force coming out of the beam, I also have a shear force and a bending moment. Look at one of the halves, sum the forces, sum the moments, set them equal to 0, and solve for those internal loads.